So let us go through with frequency modulation index. Okay, it is similar to AM frequency, but the difference here is which value we are going to use. Instead of FC, we are using FM and delta F. Okay, so in modulation index in FM is the ratio of the frequency deviation delta F to the modulating frequency FM. As you can see, delta F is equal to Kf multiplied by Vm. Okay, that is how you find delta F if only Kf and V is given in the question, and it is divided with omega m. Okay, but it can also be expressed in hertz. So m is Kf uh, multiplied by Vm over Fm in unitless value. Thus, the final equation is delta F over Fm. In modulation index, the m is equal to delta F over Fm. If you want to find the percentage, just multiply the value of the modulation index by 100%. And usually both the frequency deviation and the modulating frequency has maximum limits. Okay, this is an example 1. As you can see, it asks us to find and determine the modulation index for FM signal using this value. For question A, the modulating frequency is 5 kHz. This is our FM, while the deviation, the frequency deviation is 10 kHz. So you divide 10 kHz into 5 kHz, you will get the value 2. We do remind that modulation index does not have any units for the value because it's only looking for the ratio of the modulation. Hence, we are looking for modulation index. In question 2, the modulating frequency Fm is 5 kHz while the frequency deviation is at 15 kHz. So we divide 15 kHz to 5 kHz, we will get 3 unitless. Okay. Do note that in Fm, it is okay for the modulation index more than 1. Okay. Compared to AM, you can only have modulation index in between 0 and 1. In FM sidebands, FM and PM both produce infinite number of pairs of upper and lower sidebands. Although this means that the bandwidth is bigger, more sideband results in more immunity to loss. FM produce pairs of sidebands spaced from the carrier in multiples of the modulating frequency, and the number of significant pairs of sideband determined by the modulation index M. Okay, so the more sidebands in a signal, the less it is susceptible to noise. It has more immunity to noise. Okay, so this is an example for FM sideband where it has 6 FM value over here. Okay, as you can see, there are 3 pairs of sideband over here. We have FC plus FM and FC minus FM. This is the first pair. The second pair is FC plus 2FM and FC minus 2FM. That is the second pair. And this is the third pair, FC plus 3FM and FC minus 3FM, which result the bandwidth is equal to 6 FM. Do note that the bandwidth equal to 6 FM determines based on the diagram or sketch you are using. Okay, so since it has 3 pairs, there are 6 FM over here that you want to calculate for your bandwidth. When a modulating signal is a single sine wave, the FM equation is, it is empty over here, but in general, the equation for FM is over, which one is it? This is the one. And wait, no, that's not the one. There is one later down the road. I will show you what's the modulating signal in a single side wave for the FM later. Okay, to expand the equation in complete FM equation, including its the sideband, is difficult compared to AM. We have equation for AM is including the FC and the upper sideband and the lower sideband. Thus, for FM, we are using Bessel function to solve the equation. Okay, so this is the FM equation given by VFM. This is the FM equation. VFM equal to VC cos omega C time plus modulation index sine omega mt. Okay, by using trigonometric identities, this is the equation. The equation will become VC cos omega C time cos index sine omega m time and minus with Vc sine omega C time and sine index sine omega m time, where the cos index sine omega m time or in the first one and the sine index sine omega mt for the negative side, the other side over here, is a trigonometric series called as Bessel function. Okay, in equation 1, it is expanded using Fourier series. Thus, it becomes this equation. Okay, you do not need to worry how you get. Just try to remember where when it is even, the value for the signal is in cos value. Cos index sine omega mt is equal to J0 index plus the summation of n in even to J and m cos and wmt. While in odd, when n is odd, we are using sine instead of cos. Sine index sine wmt equal to the summation of 2j m sine and wmt. Okay, I'm sure it sounds confusing by going through the Bessel function, but once we go through the examples, you should know how to find the value later. Okay, alright. This you can try to go through yourself, or I will give a separate video later to explain this. But we will try to go through the Bessel function for FM, okay? Okay, this is your Bessel table, the Bessel function table. Do not worry, this will be given in the exam or the test for you to find the sideband pairs depending on the modulation index. Okay, let's see the first example where our index m is equal to 1. Okay, this is your modulation index. You will see the m is 1 over here. So your carrier here is 0.77 and your first, second and third will be equal to 0.44 and 0.11 and 0.02. This is how you identify the J value, the Bessel function value, using the sideband table. Okay, it's not the sideband table, it is the Bessel function table. Okay, same goes for example number 2. Your M here is 2. Okay, so you have 4 significant sideband over here, not including the carrier. The carrier is a different one. But your first one is 0.58, 0.35, 0.13, and 0.03. Okay, why this is important? Okay, the amplitude for distribution for Bessel table. When your m is 2, the other value in that row is equal to 0.22 for your carrier. Your first one is 0.58, second is 0.35, third is 0.13, and fourth is 0.03. You will write this down on the table over here. Okay, this is the diagram that you have to draw by using the Bessel function table. So we have mentioned before that the carrier here is 0.22. So your value for FC is 0.22 over here, while the others is based on the first, second, third, and fourth pair from the Bessel function itself. It is the same value and curving over here. Okay, if EC is equal to 50, as you can see from this value over here, we are trying to search for another value, the voltage value. Okay, so when EC is given 50 volts, we will use the value from J0 until J1 and J2 and J3 for your voltage value. So J0 over here is based on your, is this based on the first one? Yeah, it is. This value is used for the first modulation. Okay, it is based on example number 1 where m is equal to 1 and your carrier FC J0 over here is 0.77, J1 is 0.44, J2 is 0.11, and J3 is 0.02 over here. So EC, the 50 volts just now, is multiplied by J0, 50 times 0.77. You will get 38.5 volts, and so on by using the same equation, the same EC with different J value over here. You will get this diagram instead.